About 85% of all matter in the universe is completely invisible. We call it dark matter, and we've never directly detected a single particle of it. So how do we know it exists? The evidence comes from watching how galaxies behave. When astronomers measure how fast stars orbit around galactic centers, the speeds don't match what we'd expect from visible matter alone. The outer stars should be moving slower, but they're not. Something invisible is adding mass and holding these galaxies together. The proof gets even stronger when we look at massive galaxy clusters. Light from distant objects bends around these clusters in a way that requires far more mass than we can see. In the Bullet cluster, two galaxy clusters collided at enormous speeds, and the visible gas separated from the invisible gravitational mass. You can actually map where the dark matter went versus where the normal matter went, and they're in different places. But here's where it gets strange. A cluster called El Gordo shows peculiar offsets between its hot gas, visible galaxies, and the strongest gravitational effects. Some simulations suggest this could mean dark matter isn't perfectly collisionless after all. It might actually interact with itself in ways we don't understand. Despite decades of searching with increasingly sensitive detectors, we haven't found the particles. This has pushed some physicists toward a radical alternative. Maybe gravity itself works differently than we think, and there is no dark matter at all. What if dark matter is just a sign that Einstein's equations need an update? That's the core idea behind modified Newtonian dynamics, or MO&D. In this framework, gravity behaves differently at extremely low accelerations, like those found in the outer regions of galaxies. The theory was designed to explain galaxy rotation curves without invoking invisible particles, and it does that job remarkably well. For a long time, MOND was dismissed because it couldn't explain things like the cosmic microwave background or large-scale structure formation. But newer relativistic versions, including one called RELMOND, have started reproducing cosmological observations by introducing a new field that acts like dark dust. This blurs the line entirely between inventing new matter and inventing new physics. Even more provocative is Eric Verlin's emergent gravity hypothesis. In his model, gravity and dark matter-like effects arise from the way quantum information and entropy are distributed in space-time. Gravity isn't fundamental. It emerges from microscopic quantum interactions, the same way temperature emerges from molecular motion. If this is true, then dark matter was never real to begin with. It was just a symptom of not understanding how gravity works at cosmic scales. The debate is far from settled, but the fact that serious physicists are pursuing alternatives shows how mysterious the problem really is. In the late 1990s, astronomers studying distant supernovae discovered something shocking. The expansion of the universe is speeding up. Gravity should be slowing everything down, pulling galaxies back together. Instead, something is pushing them apart faster and faster. We call that something dark energy, and it makes up roughly 70% of the total energy in the universe. The simplest explanation is that empty space itself has energy, a kind of vacuum pressure that acts like anti-gravity. But when physicists calculate what that vacuum energy should be using quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a small error. It's the worst prediction in the history of physics. Then there's the coincidence problem. Dark energy only became dominant in the universe relatively recently, right around the time when galaxies, stars, and life could form. Why now? Why not a billion years ago or a billion years in the future? Some physicists think this points to a multiverse, where we live in one of countless universes and only notice the ones where the timing works out for observers like us. Others think dark energy is dynamic, changing over time rather than being a fixed constant. Either way, we don't know what it is, why it exists, or why it has the precise value that allows complexity to emerge. Our galaxy isn't just sitting still in space. It's moving at over 600 kilometers per second toward a region we can barely see. And this region is called the Great Attractor, and it lies about 250 million light years away, hidden behind the dense plane of the Milky Way in what astronomers call the zone of avoidance. All that gas and dust blocks our view in visible light, which gives the Great Attractor an almost ominous quality. It's a massive gravitational anchor pulling on thousands of galaxies, and we can't fully observe it. More recent surveys using infrared and radio telescopes have revealed that the Great Attractor is actually part of something much larger, the Laniakea supercluster. Laniakea contains about 100,000 major galaxies and spans over 500 million light years. Our Milky Way sits on the outskirts of this enormous structure, flowing toward its center like water draining into a basin. The name Laniakea means immeasurable heaven in Hawaiian, which feels appropriate given the scale. And even though cosmic expansion will eventually pull everything apart, Right now, we're locked in this colossal gravitational current. We're drifting through space towards structures we can't completely map, driven by invisible mass we don't fully understand. The Great Attractor isn't dangerous, but it's a reminder that even our local cosmic neighborhood holds mysteries that challenge our ability to observe and measure the universe. The cosmic microwave background is the oldest light in the universe, a snapshot of what the cosmos looked like 380,000 years after the Big Bang. According to the Standard Model, this light should look statistically random in all directions. Space should have no preferred orientation. But when scientists analyzed the CMB in detail, they found something unexpected. Certain large-scale patterns seem to align along a specific axis. This alignment was nicknamed the axis of evil, and what makes it truly bizarre is that the axis appears to line up roughly with the plane of Earth's orbit around the sun and the direction of the equinoxes. That shouldn't happen. The CMB formed billions of years before the solar system existed. There's no reason for the largest structures in the early universe to care about Earth's geometry. Some researchers think this could be caused by a primordial magnetic field that stretched across enormous scales, imprinting patterns into the CMB. Others suspect it's a statistical fluke or a subtle error in how the data was processed. Instruments like Planck have tried to confirm or rule out the anomaly, but the effect persists in some analyses. If it's real, it suggests the universe isn't as isotropic as we thought. If it's not real, it's a cautionary tale about how even our best cosmological data can trick us into seeing patterns that aren't there. At the center of every black hole, general relativity predicts a singularity, a point where density becomes infinite and space-time curvature breaks down. The equations literally stop working. But singularities are hidden behind event horizons, so we can't see them. And for decades, physicists assumed that was fine. Whatever happens at the singularity stays at the singularity. Then Stephen Hawking showed that black holes radiate energy and slowly evaporate. The radiation is thermal, which means it carries no information about what fell into the black hole. If a black hole completely evaporates, all that information is gone. But quantum mechanics says information can't be destroyed. This is the black hole information paradox, and it's one of the deepest conflicts in theoretical physics. One proposed solution is the firewall paradox. If you try to preserve information, quantum mechanics requires that the event horizon isn't smooth and empty. Instead, it's filled with a wall of high-energy particles that would incinerate anything that crosses it. That violates a core principle of general relativity, which says you shouldn't notice anything special at the horizon. Another idea, called ER equals EPR, suggests that entangled particles are connected by non-traversable wormholes. In this view, space-time itself might emerge from quantum entanglement, and black holes become windows into the quantum structure of reality. Cosmic rays are particles from space, mostly protons and atomic nuclei, that constantly bombard Earth. Most of them have low energies, but a tiny fraction arrive with energies so extreme they defy explanation. We're talking about single particles carrying as much kinetic energy as a baseball thrown at 60 miles per hour. That's a macroscopic amount of energy in a subatomic particle. There should be a natural cutoff for these energies called the GZK limit, around 10 to the 20th electron volts. Above that threshold, cosmic rays interact with the cosmic microwave background and lose energy rapidly. They shouldn't be able to travel far. But detectors like the Pierre Auger Observatory and Telescope Array have recorded particles at or above this limit, and we don't know where they're coming from. The sources are probably extreme astrophysical environments like active galactic nuclei, supermassive black holes, or gamma-ray bursts. But the acceleration mechanisms remain unclear. Some physicists even speculate whether these particles could reveal violations of Lorentz invariance or other exotic physics at energies we can't reproduce in labs. These cosmic rays are nature's most powerful particle accelerator, and they're probing fundamental physics in ways human technology can't match. Fast radio bursts are among the strangest phenomena in modern astronomy. They're intense flashes of radio waves that last only milliseconds, but release as much energy as the sun emits over several days. They come from distant galaxies billions of light years away, and for years, astronomers had no idea what caused them. Most FRBs appear once and never repeat, but some sources flare up again and again in unpredictable patterns. One repeating burst, called FRB 20201124A, showed rapid changes in its magnetic environment and polarization over the course of just weeks. That's hard to explain if the source is a simple, isolated object like a magnetar. Statistical studies of repeating FRBs also show that the timing doesn't fit neat periodic models, which complicates theories that rely on rotating neutron stars. Current leading explanations involve magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. But some bursts don't fit the magnetar model cleanly. Theorists have proposed binary systems, interactions with surrounding material, or even entirely new kinds of compact objects. Every time we think we understand FRBs, a new observation forces us to reconsider. Not all mysteries happen at cosmic scales. Some occur right here in our solar system. The flyby anomaly refers to a handful of spacecraft that experience tiny, unexplained changes in velocity during gravity assists around Earth. The effect was incredibly small, just millimeters per second, but it didn't match the predictions. Most scientists think it's a subtle error in modeling or tracking, but a few have speculated about deviations from Newtonian gravity at planetary scales. Then there's the Kuiper Cliff, a sharp drop in the number of icy bodies beyond about 50 astronomical units from the sun. Models of solar system formation predicted a more gradual decline, but the drop-off is steep. Some researchers think this is evidence of past gravitational sculpting by migrating giant planets or even a passing star. Others have suggested an undiscovered massive object in the outer solar system, sometimes called Planet 9, though no direct evidence has been found. These anomalies might turn out to be nothing, or they might be clues that even our local cosmic neighborhood still holds surprises. Either way, they're reminders that precision measurements can reveal gaps in our understanding, even in familiar territory. Physics has two extraordinary theories describing reality: general relativity for gravity and space-time, and quantum mechanics for particles and fields. Both work well in their domains but are fundamentally incompatible. At a black hole's center or during the Big Bang, both should apply, yet combining them leads to nonsense. Candidates for a unified theory include string theory, where particles are tiny vibrating strings in 10 or 11 dimensions, and loop quantum gravity, where space-time is woven from discrete quantum threads. But we lack experimental means to test these ideas. The energies required are beyond current labs. Even within quantum mechanics, unresolved mysteries remain. The measurement problem questions why quantum systems exist in superpositions until observed and what constitutes an observation. Bell's theorem shows that quantum mechanics is non-local, with entangled particles affecting each other instantly over vast distances. Some physicists believe space-time and gravity might emerge from quantum entanglement, linking cosmological mysteries to quantum puzzles. The universe is far stranger than it appears. From invisible matter shaping galaxies to quantum paradoxes and black holes, these mysteries are active frontiers where our best theories break down and new physics awaits. For more deep dives into science's wildest corners, check out this video next. Thanks for watching.